Hi everyone, this is amount of substance for A-level chemistry. Let's get right into it. So you need to know about two definitions. These are relative atomic mass, the AR, which is the average mass of an atom of an element on a scale where the mass of an atom of carbon-12 is exactly 12, and the relative molecular mass, MR, which is a similar definition but in terms of molecules. The average mass of a molecule on a scale where the mass of an atom of carbon-12 is exactly 12. And the MR is referred to as the relative formula mass for ionic and giant covalent compounds. So Avogadro's constant, L, is the number of particles in 1 mole. This number will be given in the exam, and it's 6.022 times 10 to the 23. So if you'll need to use it in the question, it'll be specifically given to you. So what is the mole? Well, you should know, but the mole is simply a specific number, and it's used as a measure of the amount of something in chemistry, which could include electrons, atoms, molecules, or ions. So you need to know about the following key equations for this topic, which is going to be moles equals mass over mR, with the mass in grams. Just know that it says mR there, but that could equally be AR if we're working out the number of moles of an element. We also have N equals CV, moles equals concentration times volume. Your concentration is in moles per dm cubed, and your volume is in dm cubed. Number of particles, which is moles times Avogadro's constant, so NL. And we have something called the ideal gas equation here. This is PV equals nRT. So pressure times volume equals moles times R, which is something called the gas constant, times temperature. And the units are pressure in pascals, volume in meters cubed, moles in moles, the gas constant, and the temperature in Kelvin. So the gas constant, just like the Avogadro's constant, will be given to you in the exam, so you don't need to know it. And its units are joules per Kelvin per mole. Next, percentage yield is the actual yield over maximum theoretical yield times 100. That should be familiar from GCSE. And also familiar should be percentage atom economy, which is MR of desired product over MR of all the reactants times 100. This could also be MR of all the products rather than reactants as well. So, yeah. So now for some unit conversions. Right. So I'm going to just state the obvious. 1 kilogram is 1,000 grams, and 1 kilopascals is 1,000 pascals. Kilo means 1,000 or something. You should know that. But now onto the units of volume, which are a bit more obscure. 1 decimeters cubed, dm cubed, equals 1,000 centimeters cubed. 1 meters cubed, however, is equal to 1,000 decimeters cubed. So to convert from meters cubed to dm cubed, or vice versa, you want to multiply or divide by 100. Okay? You multiply or divide by 100. And that's the same if you wanted to convert from dm cubed to centimeters cubed. To convert from meters cubed directly to centimeters cubed, or vice versa, you're going to have to multiply or divide by 10 to the power of 6. So just remember it's 10 to the power of 6. If I was converting from centimeters cubed to meters cubed, I would times my value by 10 to the minus 6, because that would be the same as dividing by 10 to the 6. And if I wanted to convert from meters cubed to centimeters cubed, I would times my value by 10 to the 6. Up here, if I wanted to convert from meters cubed to decimeters cubed, I could times by 10 to the 3, because 1,000 is also the same as 10 to the 3. If I wanted to convert from dm cubed back to meters cubed, I would multiply by 10 to the minus 3. So now for units of temperature. To convert from degrees Celsius to Kelvin, you have to add the number 273. So you just have to memorize that. Next, we have state symbols. These are included next to substances in reaction equations to indicate their physical state. So we have S for solid, L for liquid, G for gas, and AQ for aqueous, which means dissolved in water. Right, before we get into the more complicated stuff, just a quick review of balanced and ionic equations. So balanced equations have the same number of atoms of each element on each side of the equation. And equations are balanced by changing the number in front of chemical formulae. So here's an example. This is the equation here. It's not balanced, but if we add 6's onto everything except from this glucose molecule, then the equation ends up being balanced. And you can just pause the video and check that for yourself. To balance equations, you're just going to have to use trial and error. It's just something you'll get quicker with practice. So next, ionic equations show only the species which react. And to deduce an ionic equation, we write out the equation, but split any aqueous ionic substances into their constituent ions. And you then cancel out any species which appear on both sides of the equation. So we have an example we'll work through here. So we've got barium chloride plus iron sulfate forming barium sulfate plus iron chloride. So the first step is to split any aqueous ionic substances into their constituent ions. So we can see that barium chloride here is aqueous. We can split that into its constituent ions here. Iron sulfate is also aqueous. We'll split that into its constituent ions. Barium sulfate is solid, so we're going to leave that as it is. And then iron chloride is aqueous, so we'll split that into its aqueous ions. Second step, we're going to cancel out any ions that appear on both sides of the equations. The ions we cancel, we call spectator ions, because they are the ones that are not involved in the reaction. Okay, they don't change. They're just there, spectating, if you like. So we can see that the chloride ions, we have two chloride ions on both sides of the equation, so we're going to cancel those out. We also have an iron ion on both sides of the equation, so we'll cancel those out too. And we'll be left with this. We've got barium ions plus sulfate ions forms your barium sulfate, and you can add the state symbols back in. Okay. Right. Using molar ratios. So this is a pretty general slide. Everything on this slide is going to apply to many different parts of this topic, because this is a very central concept in A-level chemistry. Okay. So the numbers in front of substances in reaction equations can be compared with each other, and the deduced molar ratio can be used to calculate the number of moles of one substance from the number of moles of another substance. And this number of moles can then be used to calculate a specific value, such as the mass, concentration, or volume of that substance. So we've got an example here. 0.02 grams of sodium reacts with excess hydrochloric acid. Calculate the volume in centimeters cubed of hydrogen gas produced with a pressure of 100 kilopascals at 25 degrees Celsius. So for any question like this, our first step would be to write out the balanced equation. So we've got sodium plus hydrochloric acid forming sodium chloride plus hydrogen. And we've balanced it by putting half in front of this hydrogen here. So we then work out the molar ratio. Sodium to hydrogen is going to be our molar ratio we're interested in, and that's 2 to 1. Then we calculate the number of moles of sodium. The reason why we don't do it for hydrochloric acid is because we're told it's in excess, which means that any change in the number of moles throughout the reaction of hydrochloric acid would be insignificant. So sodium is our limiting reagent, and that's what's going to affect the yield of hydrogen, and that's why we calculate the number of moles of sodium, not hydrochloric acid. So we're going to use our equation moles equals mass over mR, which gives us a value of 0.04. Step 4, we use this value and the molar ratio to work out the number of moles of hydrogen gas. And so we'll divide it by 2 to give us a value of 0.02, and that's because our ratio is 2 to 1, okay? Our fifth step is that we use the number of moles of hydrogen gas to work out its volume. So the first step is going to be our unit conversions. So our pressure, we've been given our pressure in kilopascals, but we need it in pascals. So if we times by 10 to the 3, we'll get our pressure in pascals, 100,000. Now for the units of temperature, we've been given it in degrees Celsius, but we need it in Kelvin, so we're going to add 273 to 25, which is 29 Kelvin, okay? Then we're just going to substitute our values into the rearranged equation of PV equals nRT for volume, which gives us a value of 4.95 times 10 to the minus 4 meters cubed. So, the question, we're not done yet because the question wants this volume in centimeters cubed. The ideal gas equation gives us our volume in meters cubed. So to convert from meters cubed to centimeters cubed, we're going to times our value by 10 to the 6, which gives us a final answer of 495 centimeters cubed. So this general method is going to work no matter what value the question asks you, to work out, whether it's volume, mass, concentration. The only step that's really going to differ is the fifth step, which and what equation you're going to be using. Okay, it's the same concept. So now for empirical and molecular formulae. So another two definitions you need to know: empirical formula, which is the simplest whole number ratio of atoms of each element in the compound, and molecular formula, which is the actual numbers of atoms of each element in the compound. The molecular formula of a compound can be calculated from its empirical formula and the MR of that compound. So here's an example. So we've got the empirical formula of a compound with an MR of 84 is CH2. The juice's molecular formula. So for step 1, we're going to be calculating the MR of the empirical formula, which is sometimes called the relative empirical mass. So we're just going to do 12 times 2 times 1, which gives us 14, right? The second step is we're going to work out a scale factor, and to do that, we're going to divide the MR of the actual molecule by the relative empirical mass, okay? So 84 divided by 14 gives us 6. So 6 is our scale factor. The third step is that we then multiply each element in the empirical formula by this scale factor to deduce the molecular formula. So we've got CH2, okay? So we're going to be doing, so we've got one carbon, we'll do 1 times 6 carbons, and we've got 2 hydrogens, so we'll do 2 times 6 hydrogens, which gives us the final answer. Our molecular formula is C6H12, which is hexene. Right, so now into something that's a bit trickier. The empirical formula of a compound can be calculated from data given percentage by mass. So this is best explained with an example. So a compound contains 56.5% potassium, 8.7% carbon, and 34.8% oxygen. The juice's empirical formula. So the first step is that we're going to assume we have 100 grams of this compound, because that would make the percentages up here equal to the mass, of each element present in the sample. So as we can see, if we assume we've got 100 grams of sample, then we're going to have 56.5 grams of potassium, 8.7 grams of carbon, and 34.8 grams of oxygen. Okay. Then we want to work out the number of moles, so we're going to divide each mass by the AR. Okay, and this gives us our number of moles. The second step is that we divide each number of moles by the smallest number of moles calculated to find the ratios of elements, right? So we're going to divide each number of moles up here by the smallest one, which you can see to be 0.725. So we'll divide each number of moles by 0.725, which gives us ratios of each element, which is 2 potassium to 1 carbon to 3 oxygen, right? So the third step, this doesn't apply to this question, but for in the exam, you might not get these ratios as whole numbers. So what you would do is that you would multiply each ratio, so all these ratios, by the same integer. So that would be 2 if the ratio is around 0.5, or 3 if the ratio is around 0.33, okay? Because that would make them close to whole numbers again. So in this case, they are already, right? So we don't have to do this step. So the fourth and final step is that we use this ratio, the new ratio, or the current ratio for this question, to write the empirical formula. So our ratio of potassium to carbon to oxygen is 2 to 1 to 3. So our empirical formula will be K2CO3. So potassium carbonate. You could also be required to deduce the empirical formula of a compound from experimental data given composition by mass. So this is a little bit trickier because you actually have to think about what's going on a little bit. So here's an example, quite a common one in the exam is to ask you to do this from a hydrocarbon, alright? And so it's definitely worth learning this specific method. So the complete combustion of a hydrocarbon produced 4.4 grams of carbon dioxide and 1.8 grams of water. Deduce the empirical formula of the hydrocarbon. So, as I said, all the steps are the same except you're calculating the number of... Well, I didn't say that. All the steps are the same except you are calculating the number of moles of carbon dioxide and water. Right, so you're not calculating the number of moles of carbon and hydrogen yet. You're working out the number of moles of carbon dioxide and water, So, 1 mole of water contains 2 moles of hydrogen atoms, which must have come from the hydrocarbon. So we multiply the number of moles of water by 2, as this gives us the number of moles of hydrogen atoms in hydrocarbon, so it'd be 0.2, right? 1 mole of carbon dioxide contains 1 mole of carbon atoms, which also must have come from the hydrocarbon. Therefore, the number of moles of carbon dioxide is equal to the number of moles of carbon atoms in the hydrocarbon. So that's 0.1. We don't have to do anything. Then we just proceed as normal. We work out the ratios. We divide them by the smallest number. Which is just going to still be 1 to 2, which gives us an empirical formula of CH2. Right. So that's that. So a little bit more about atom economies. You need to remember to always account for the numbers in front of formulae in the reaction equation. So I'll show this with an example. So we've got the equation for photosynthesis here, and we want to calculate the percentage atom economy for the formation of glucose. Okay. So the first step is that we're going to calculate the MR of each reactant and the desired product. All right. So no timesing by the numbers in front of the formula yet. We're just going to calculate the MR of each reactant and desired product. Right. Second step. Now we're going to multiply the MR of any species with a number in front of it. Okay. So for carbon dioxide, we times in its MR by 6. Water will be times in its MR by 6. But glucose, it's 1. We can leave it as it is. Third and final step, we'll substitute the values into the equation of percentage atom economy, times it by 100, and we've got 48.4%. So not particularly high. You need to know why it's important that chemical processes have a high atom economy. So it's for the following reasons here. So they use up non-renewables more slowly, so they're more sustainable. They're cost effective as they require less raw materials. They produce less waste and pollution. Less money is spent separating the waste from the desired product. And the price of medicines and other consumer products are reduced as their manufacture is cheaper, making them affordable to a wider range of people. So we have ethical, financial, and environmental reasons for why we want to do this. Right, so now for required practical 1. This is acid-base titrations. So this practical consists of 2 parts. The first part is making a standard solution, also called a volumetric solution, which we'll use in the second part, which is the actual titration. And what a standard solution is, it's a solution with a known exact concentration. So this is how you make one. You need to know how to make one. It's a common question in exams, 6 marker. Easy 6 marks, alright? So, first step, place a weighing boat on a digital balance and measure out a set mass of solid. Record the total mass of solid and the weighing boat. Second step is that we tip the solid into a beaker of distilled water. We stir with a glass rod until the solid has completely dissolved. We then reweigh the weighing boat and subtract this mass from the solid and weighing boat together, which we got here, to obtain the precise mass of solid added to the beaker. And that's because when we tip the solid from the weighing boat into the beaker, there's still going to be some left behind on the weighing boat, so we need to account for that, okay? So, fourth step, we use a funnel to transfer the solution we made in step 2 from the beaker into a volumetric flask. We then wash the beaker, glass rod, and funnel with distilled water and add the washings to the volumetric flask. That's because there's going to be some solution clinging to this equipment, okay? And we want to get all of it into our volumetric flask to increase accuracy. So, fifth step is how we add distilled water to the volumetric flask until the bottom of the meniscus is under graduation. So, you should know what the meniscus is, but I'll briefly just explain. First of all, a volumetric flask has a, it's like a little bulb down here with a very long neck. And in this neck here, the solution is going to be slightly curved, slight dome shape. And we also, we always measure from the bottom of that curve. That curve is a meniscus. We measure from the bottom of the meniscus, okay? So our final step is that we stop at the volumetric flask. And we invert it several times in order to mix well. So now for the actual titration bit. Firstly, the apparatus. Down here I'm showing a pipette with a pipette filler. So that's your pipette. Your burette is up here. We position that using a clamp stand. We've got a conical flask here and we've got a tile here. So the difference between a pipette and a pipette only measures one volume of solution. You get different sized pipettes for different volumes. You'll probably use either a 10 or a 25 centimeters cubed one. This one looks like it's about 5 centimeters cubed. And a burette allows you to measure different volumes of solution. And it allows you to add the solution in the burette to another solution at different rates using this tap here, which is called a stopcock. Right. So how do we actually carry out an acid-base titration? Well, we use a funnel to fill a burette below eye level with a standard solution of alkali. We then remove the funnel and ensure the jet of the burette is filled. We then record the initial volume of alkali in the burette. So in this method, we've got an alkali in our burette, which we're adding to a acid in a conical flask. And the alkali has a known concentration and the acid has an unknown concentration. However, you could also titrate an acid with an alkali. You could also titrate an alkali in a conical flask with an acid. And also, the unknown concentration could be the way around. You could have an unknown concentration of alkali, right? So this is just a general method. So we then use a pipette and a pipette filler to add a set volume of acid with an unknown concentration to a conical flask on a white tile. So the reason why we use a white tile is because that allows the colour change in the next few steps to be seen more clearly. We then add a few drops of a suitable indicator to the conical flask. So suitable as in it needs to change colour over a very narrow pH range. Universal indicator wouldn't be suitable because its colour change would be too gradual, which means we couldn't accurately determine the endpoint of the reaction. We then carry out a rough titration by adding the alkali to the acid using the burette, swirling the conical flask regularly until the solution changes colour, so that's the endpoint. We then record the final volume of alkali in the burette and calculate a rough titer. So we do that by subtracting the initial volume from the final volume. So final volume minus initial volume will give us a titer. Then we carry out an accurate titration. So we do this, step 4, but we're going to add drop-wise towards the endpoint. So around 2 centimeters cubed from the endpoint, we're going to start adding it drop-wise. So the purpose of this rough titration was to, determine around where the endpoint would be. Step 6 is we're going to repeat until at least 3 concordant titers are obtained, and we're going to calculate the mean titer. So what concordant means is usually within 0.1 centimeters cubed of each other. We then use the mean titer to calculate the unknown concentration of the acid. So this is what titrations allow us to do. They allow us to titrate one substance, with a unknown concentration with a substance with a known concentration, and that allows us to work out the unknown concentration, right? Titration calculations. These link to the idea of molar ratios. Exact same method, except we're using a different equation for step 5. Okay? So, here's an example. 37.5 centimeters cubed of 0.1 moles per dm cubed NaOH was required to neutralize exactly 25 centimeters cubed of HCl with an unknown concentration. Calculate the concentration of HCl. So, first step, we're going to write out a balanced equation. This is our simple acid plus alkali form salt plus water. So, step 2, we're going to deduce the relevant molar ratio. So that's going to be sodium hydroxide to hydrochloric acid. We can see from the equation it's 1 to 1, which means that the number of moles of sodium hydroxide is going to equal the number of moles of hydrochloric acid. Okay? But let's work out the number of moles of sodium hydroxide. It's going to be 0.1 times 37.5 times 10 to the minus 3. That's because we're using the equation N equals CV. And our volume needs to be in centimeters cubed, our volume needs to be in decimeters cubed, not centimeters cubed. So we'll be dividing, we'll be dividing it by 1000. Okay. Step 4, we're going to use this value to deduce the number of moles of HCl. We already talked about this 1-to-1 ratio. It's going to be the same. Okay. So now, finally, we're going to rearrange the equation N equals CV for C. And we're going to calculate the concentration of HCl. So concentration equals moles over volume. We'll do our moles over our volume, again remembering to convert it to dm cubed, which gives us a final answer of 0.15 moles per dm cubed. So that's it for amount of substance, guys. The only real way to get good at this topic is to just continue to do practice questions. This was just a summary of everything you need to know content-wise. Thanks for watching, and I'll see you for the next one.